So today we're going to jump a little bit more into exponential functions. You've studied these before, so it's going to be kind of like a little bit of a review / talking more about what the pre-cal aspects of functions are, some things maybe you didn't talk about before. But exponential functions are not necessarily new for you. They're in Algebra 1 and Algebra 2 curriculum. They're also going to be the type of function you actually see in real life, and that's not like the math teacher making up like you buy 18,000 watermelons at a store. No, you actually see exponential functions happening naturally in the real world. We just experienced a pandemic. The way that diseases spread across the world is spreading exponentially. So this is actually things you're going to see. I'm not lying to you. When we get to actual applications of these things, these are real life applications of functions. But to kind of make it so your brain follows, we've studied linear functions for forever. Linear functions look like lines. Check, we got it. Quadratic functions have parabola shapes, the U's, because of the squared term. And exponentials are going to be curves, so they're not straight lines and they're not U's. But they are going to grow or decay exponentially the entire time across their domain. Okay? The way we know we're dealing with an exponential function is that you see that there is an x in the exponent, which is why we call them exponentials. So the moment you have an exponent that is a variable, you are dealing with an exponential function. These are our geometric sequences, but we get to play connect the dots this time to create actual functions. Like I said earlier, exponential functions are some of the most important functions in the real world. They appear in many places, including population growth, money, okay, radioactive decay, spread of diseases, etc. In addition, the old SAT, and I'm not sure if this is still correct on the new SAT because we know it's been rewritten, we've been studying for that, will include several questions that require understanding of exponential functions. So we take our PSAT on Thursday, so we should know more information after we have more practice exams. But typically on the old SAT, this was one of the types of functions you could be exposed to. So let's talk about some key characteristics of this exponential graph and the exponential function itself. So the exponential function has a general form, so it's like parent function, sort of, is f of x equal to a times b raised to the x power given that b is greater than 0. So for all real world scenarios, b is going to be greater than 0. Now, if we're like, which one's b? We're talking about the rate. Now, if you think about one of the problems we just did on our quiz, our rate was a negative number. That's because theoretically it could be negative. So if we have a math-only context for a problem, the b value technically could be negative. But for real world things, the b value is always going to be positive. It's going to be above the x-axis. A represents what's called the initial amount. So that's this value here. That's my initial amount. That makes sense because that was our starting term in our sequence. That's our initial amount. It's our y-intercept. The b represents a few things. So it has a bunch of different names, and I unfortunately use them interchangeably because that's just my habit. We can call it the base. That's why it's a b for base. We can also call it the common ratio, which is what we called it when we were talking about sequences. Or you can call it the factor with which our graph is growing or decaying. Now again, I use all of those words interchangeably. I probably use base and factor the most, but we're still talking about that b value, whatever number is raised to an exponent. So there are two general types of exponential functions. Again, these are the ones that actually happen in real world. Theoretically, they could look two other ways, but in real life, this is really the way they're gonna go. You have exponential growth. What do we notice about the growth graph? It's going up. This is where things get bigger exponentially, which means they get bigger very, very quickly. For exponential growth, your a value is greater than 0, meaning your y-intercept is greater than 0, and your base, your factor, is greater than 1. Meaning that you have an improper fraction or a number bigger than 1 inside your parentheses so that the number gets bigger. So big number gets bigger. That checks out. For exponential decay, pretty much everything is the opposite except for your a value. Again, when we're talking about decay, the graph's getting smaller and smaller every time. It's still above the x-axis, so that a value is going to be positive. Theoretically, it could be negative, but that doesn't really happen in real life. These are the two most common types of exponentials you will see. But important here, the b value is between 0 and 1. It's really tempting to say that it's less than 1. Again, that's a different type of exponential. We're just talking about when it is a true fraction, like 1/2, 1/3, 4/7, something that's an actual true fraction less than 1. Notice it also cannot be exactly 0, because then it would be 0 to some power, and 0 to any power is 0, which would be a constant function. I digress. Some more things about the exponential function, kind of bringing in some vocabulary we learned about for other functions. We have increasing and decreasing. If you notice, exponential functions are always either increasing or decreasing, and it has to do with whether it's growth or decay. They will never switch from one to another, so they go one direction the entire time. That means that they will not have any extrema, because you're never changing from positive to negative. Slope, air quotes, it doesn't actually have a slope, but we can find an average rate of change. Additionally, when we talked about concavity way back when, concave up was the types of graphs that looked like this. So I have the concave up graph with my hands. Opening up is concave up. They're always going to be concave up or concave down. In real life, the real life ones we have on our paper, they're both concave up. So we're going to see those a lot more often. But theoretically, we can also have concave down graphs. We will see those later. They're just not as common. But they will always be either one or the other. They never switch concavity. And since they never switch concavity, that means that they have no points of inflection. So while with quadratics and polynomials, I was able to ask you a bunch of different types of questions in regards to points of inflections, concavity, all that stuff, and they were difficult to see. These are going to be really simple because the shape doesn't really change the entire time. It's always going to be either increasing or decreasing, and either concave up or concave down, mostly concave up. Now tying in some more vocabulary we've had before, end behavior. End behavior is talking about what's happening at the end of the graph. Okay, for exponential functions, the input value, as the input values increase or decrease without bound, the y values will either increase or decrease without bound or approach 0. So let's talk about the two most common, again, these are our most common growth and decay and what their end behavior would be, just to make sure it makes sense to us. For our growth graph, as we look on the left side, what's happening to the y values as you go to the left? What is it approaching? What's it getting flat to? 0. If we remember back to when we took Algebra 1 and Algebra 2, there is a horizontal asymptote there at the bottom that you're not allowed to touch. But we're going to get mighty close to it, which means it's approaching 0. That's its limit. But as we look on the right side, where is that graph headed? Up to infinity. So for our growth graphs, which is where b is greater than 1, you're going to have this limit statement for your end behavior. But if you have your decay function, because it kind of switches, as you go to the left, what's happening with my y values? It's going up to infinity. And what's happening with my y values? Oh, sorry, I said that all wrong. What's happening to my y values as I go to the right? It's going up. That's the left. Oh my gosh, we're going to call that a Monday problem. What's happening as I go actually to the right? What is it getting flattened out to? 0. Again, because we have a horizontal asymptote there, it's a boundary line the graph cannot cross. That's just information from Algebra 1 and 2 that we needed to have remembered. Now again, there are two other types when that graph is reflected over the x-axis, but in the real life problems we're going to see most often, we don't see those. But we will see them in just some general regular math problems. So flip it over. Let me tell you the types of questions I might ask you today, because we're just discussing this vocabulary and applying it to exponential functions, these characteristics. So first things first, we're going to write some limit statements. We've gotten better at limit statements as we've gone, but let's make sure we still got it. For this graph right here, if I ask you for the limit statement on the left, you would say the limit as x approaches what number to indicate you're talking about the left side? I think I heard somebody say it, but it also was really quiet. Okay, yeah, negative infinity. Now we'll just pretend this function is named f of x. They didn't tell me what it was named. Now what's happening to that graph as we go to the left? What is it getting closer and closer to? 0. So the limit as x approaches negative infinity for f of x is 0. What's happening on the right side? The right side would be the limit as x approaches positive infinity for this function f of x. Where are those y values going? Infinity, because they're going up. That is going to be, again, one of my exponential growth equations, because it's growing as x grows. Now, B is a shape we haven't seen yet before. This is one of those theoretical ideas. Won't really see this in real life, but we can still talk about it in theory because we're just asking about the end behavior. To talk about the left end behavior, we say the limit as x approaches negative infinity. Again, we'll name this function f of x again. Didn't tell us its name. What's happening on the left side, though? So what kind of infinity is it? Negative infinity, yeah. That's not going to be common in the real life ones. Shouldn't really see it in the real life ones, but in theoretical math problems, it can still, limit can go to negative infinity. But on the right side, so as x approaches positive infinity, what is my function getting closer and closer to? 0. Because we have the horizontal asymptote at the x-axis at y equal to 0. Now from a graph, real simple, yeah, because we're just looking at the shape. Without graphing, how can we tell what the end behavior would be for this function? There's two things I need you to look at for that to happen. Number one, I need us to know where our y-intercept is. Our y-intercept is always that first number that does not have a power attached to it. So if I were to just quickly sketch this on a graph, would that y-intercept be above or below the x-axis? Above. Fabulous. Here's 5. We know that that's where the graph's going to cross the x-axis, so we know it's all going to be above the x-axis since you can't cross it. The other thing we need is this ratio, is the factor, is the base. What kind of fraction is that? Is that fraction bigger than 1 or less than 1? Less than 1. So we know that this is going to be a decay function because this b value, 2/3, is bigger than 0 but less than 1. It's a true fraction. That's what I like to call them. If it's a true fraction, we know it's decay, which means that we know that the shape should decay. But it has to touch that y-intercept, so we know it's all above the x-axis, but decaying. So from those two numbers, I know the shape of this graph. I know that on the left side, as we approach negative infinity, this function, this one's called g of x, would be going up to positive infinity. And I also know, because it's a decay function, that as we go to the right for g of x, what is my value? My y value is going to be approaching 0. So again, this one is really easy to figure out the shape. You just need two numbers. You need to know if it's above or below the x-axis to start on our y-intercept, and if it's growing or decaying, getting towards the x-axis or away from the x-axis. Pretty simple, yeah? Sure. Thank you for your honesty. For part A of an example 2, this one we're just determining if the function is increasing and decreasing and concave up or concave down. So we're just going to circle our answers here. For part A, really simple, don't overthink it. Is it increasing or decreasing? Decreasing. Fabulous. Now using your hand shapes for concavity, is this concave up or concave down? Concave up. The hand shapes are really going to save you on concavity. What about B? Is that increasing or decreasing? Decreasing. That was an unconfident answer on decreasing, so let me tell you why. Please ignore my drawing skills. If you were a little stick figure walking along this graph, would you be going uphill or downhill? Downhill. That means it's decreasing. That's the easiest way for me to think about it. Sometimes I draw little stick figures on my things. Now, using your hands to tell me about concavity, is this concave up or concave down? Concave down. Fabulous. Ooh, and now we weren't given a graph, but no worries. We still know how to create the graph shape in our head. The same way we did it a second ago, we do the same thing. Okay, the y-intercept, is it above or below the x-axis? Above. So I know generally it's going to be like here-ish. We'll say that's 3. Now from my ratio, from the rate, from the factor, the number with the exponent, is this going to be growing or decaying? Growing. Oh, I totally missed. Let me try that again. All right. We know that this is going to be growth because the b value 4 is greater than 1. If the number that's in the parentheses is greater than 1, it's growing. So we know the actual shape here. Is this increasing or decreasing? Growth is always increasing. Cool. Is it concave up or concave down? Concave up. We were ready for that one. Nice. So again, you're checking your y-intercept and your growth factor or decay factor to decide what the shape looks like so you can answer questions. Now the third question here is kind of putting a lot of things together that we've done before. It says the selected values of the function f are shown in the table below. We're going to determine now not only if it's linear or quadratic or any other degree of polynomial, which we've done before, but also if it's potentially exponential. So to do that, we first of all check just to make sure that the x values are going at a normal pattern. Are these x values changing at the same pattern the whole time? Yeah, they're doing +5 the whole time, yeah? Okay, so we're good to just do like the little change in the tables. So just like we've done for forever, let's do this change. How do you go from 3 to 5?
2.
How about from 5 to 9?
3.
9 to 17? And then 17 to 33.
16.
Really obvious answer here. Are those the same number? No. Our first differences were how we decided if it was linear. So it's definitely not linear. How did we decide if something was quadratic? The second differences. So we do the differences of the differences. How do I go from 2 to 4?
2.
How do I go from 4 to 8? How do I go from 8 to 16? Again, this is a simple answer. Are those all the same number? No, so our quadratic second difference was also not the same. Darn. All right, so that didn't work. It's definitely not linear. It's definitely not quadratic. The third option is exponential. How can we check to see if a table has values that are exponential? Multiplication and division. Fabulous. So this is what we did before with our sequences. I'm not going to erase all this because I think it's important to have. I'm just going to like restart over here. If I go from 3 to 5 using multiplication or division, what am I multiplying by? Ooh, that's a good question, huh?
0 point something.
It is a, yes, but it is a fraction. 5/3. Second term divided by first term, reduce it if possible. Okay, cool. How do you go from 9 to 5? Anybody else just start singing the Dolly Parton song to themselves? No, just me? Okay, 9/5. How do I go from 9 to 17? 17 over 9. And we're getting it now. How about from 17 to 33? Really easy question here. Are those the same numbers? No. When we tried to do multiplication, I guess I should put this multiplied sign here so we see that's what we're doing. And it doesn't give you the same common ratio the whole time. That means it does not even have a factor that is the same. Okay, those are the only ones the question asks us to try. So we're like, well, it's none of those. So here's how we answer the question because we're going to start using the correct vocabulary in our sentences. We would say none of the above because, and then we're mirroring the sentences we wrote last class. None because over equal length, input value intervals, the output values of f of x do not change at a constant rate of change or proportionately. I spelled that word wrong literally all the time. Nor, because we checked 3 things this time. That would just be talking about the 2 things we checked. Constant rate checks for linear. Proportionality checks for exponential. The way we write the sentences that tell us we're talking about quadratics is that the NOR is the change in the rate of change constant. And I went back and looked, here's just some behind the curtain. I went back and looked at one of our test questions from test 1 in this class. And it was a question that had a table that asked you, is it linear or quadratic and why? 90% of the class could tell me it was quadratic. But about 50% of the people who told me it was quadratic told me the wrong reason. So this is the reason we're looking for. And I'm going to color code these so you know what I'm talking about. If we're talking about the just constant rate, we're talking about the linear change. So just the changing at a constant rate. That's a slope. If we talk about proportionality, we are talking about exponentials. But if we want to talk about something for a quadratic, we are talking about the change in the rate of change. That was going to be the words that you're looking for to talk about something being quadratic, that the change in the rate of change is constant, which is a lot of words that sound very similar. Change in the rate of change is constant talks about quadratic. So we were unclear with that back in Unit 1, Part 1, which is why we're bringing this vocabulary back. So there's 3 reasons you can give me for your tables. If it changes proportionately, that's exponential. If it changes at a constant rate, that's linear. If the change in the rate of change is constant, that's the second difference, then it's quadratic. Are we pretty familiar with exponential functions? I feel like we've studied them enough in other classes where the shape is not all that shocking, but we hadn't really talked about this vocabulary in regards to them.